Right now, without deciding to, you are running a measurement that the finest laboratories can only perform near absolute zero, sealed in a vacuum with room-sized instruments. You are running it in the warm, wet dark behind your face several times every second, and you have never once noticed. Take a breath through your nose. In that quiet instant, something in your head sorted a drifting cloud of molecules and handed you a feeling. Coffee, rain, smoke, before you could form a word. It felt like nothing. It may be one of the strangest things your body does. Stay with me, and you will understand why the ordinary act of noticing a smell may reach into the deepest and most unsettling layer of physics we know, and why, after nearly 90 years of argument, some of the sharpest minds in science still cannot agree on how you just did it. There are two rival stories of how smell works. The first is comfortable. Your nose feels the shape of a molecule the way a lock feels a key. The second is not comfortable at all. It claims your nose does not read shape. It reads vibration, listening to molecules tremble. And somewhere in that reading, a single particle slips through a wall it should never cross. By the time this is over, you will know where that idea came from, why brilliant people call it impossible, why others cannot let it die, what a mirror molecule and a heavier hydrogen reveal, and why the physics in your nose may be the physics we use to read the chemistry of dying stars. If you find value in explorations like this, the subscribe button quietly helps these deep dives reach more curious minds. So, here is where it begins, with a breath and a mystery. Begin with the thing itself, a smell. A molecule lifts off the surface of warm bread, or a cut lemon, or the skin of someone you love. It tumbles into the air, one among uncountable others, and rides a current of breath up into the narrow roof of your nasal cavity. There, on a patch of tissue no larger than a small coin, it meets a living surface studded with nerve endings. Different sources place the olfactory epithelium at somewhere between 1 and 10 square centimeters, and even that is disputed. Around 5 million olfactory sensory neurons wait there in the dark, their delicate hairs bathed in mucus. The molecule dissolves, drifts, and touches one of them. In that touch, a signal is born that will become, a few hundred milliseconds later, the feeling you call a scent. That is the sense of smell. The oldest sense, older than sight, older than hearing, inherited from creatures that had no eyes at all. For all its age, it is the sense we understand least. We can tell you in exquisite detail how the eye bends light and how the ear sorts frequency. We cannot tell you, with anything like the same confidence, how the nose knows what it has just met. Here is what is not in dispute. In 1991, two researchers at Columbia University, Linda Buck and Richard Axel, published a discovery that reorganized the entire field. They found the genes, a large family of them, that build the detectors inside the nose. These detectors are proteins called odorant receptors, and they belong to a vast and ancient class of molecular machines known as G-protein-coupled receptors. The body uses that same broad family to sense light, hormones, and neurotransmitters. Buck and Axel first identified a handful of these odor genes and estimated the family might run to 1,000. In humans, the number of working receptors is now put at roughly 400. For this work, for revealing the receptors and the logic of the olfactory system, they received the Nobel Prize in Physiology or Medicine in 2004. So we know the hardware. When an odorant meets its receptor, the receptor changes shape. That change activates a partner molecule inside the cell, a specialized G-protein. The G-protein switches on an enzyme. The enzyme floods the cell with a small messenger molecule. That messenger opens channels in the cell membrane. Ions rush in. The neuron fires. A chemical event at the surface becomes an electrical pulse racing toward the brain. Odorant, receptor, G-protein, enzyme, messenger, channel, spark. That cascade is textbook. You will find it in every neuroscience course on Earth. And yet, what does it mean that we can diagram every step of that signal and still not know what the receptor recognizes at the very first step? Notice the sentence at the center of it. When an odorant meets its receptor, the receptor changes shape. Everything downstream, the cascade, the spark, the scent, depends on that first recognition. The receptor has to know it has caught the right molecule. This is the question the textbook does not settle. Not how the signal travels, how the recognition happens. What exactly does a receptor detect when it detects a smell? For most of the last century, the answer seemed obvious, and it is still the mainstream answer today. The receptor detects shape. This is the lock and key theory, the docking theory, sometimes called the shape or odotope theory. A chemist named John Amour gave it its clearest early form in the early 1960s, and it fit the receptor discovery of Buck and Axel so naturally that the two became almost a single idea. A molecule has a shape, a particular arrangement of atoms in space, a contour of bumps and hollows and electric charge. A receptor has a pocket. When the molecule fits the pocket, the way a key fits a lock, the receptor closes around it, changes conformation, and fires. Smell, on this view, is touch at the molecular scale. You are feeling the geometry of things too small to see. It is a beautiful theory, and it has enormous support. In 2023, a team led by Christian Billesböhler and Ashish Manglik at the University of California, San Francisco, did something the field had waited decades for. They used cryo-electron microscopy, a technique that flash freezes molecules and photographs them with electrons. And they captured the first clear structural image of a human odorant receptor. It was one called OR51E2, caught in the act of holding its target, a small molecule called propionate, the sharp note in aged cheese and sour milk. There it was. The odorant sat inside an enclosed pocket, held by a tight cage of surrounding atoms. The authors describe the selectivity as controlled by tight packing interactions, a key in a lock. The picture that most researchers had believed for half a century now had a portrait. If the story ended there, it would be a clean and satisfying chapter of biology. A molecule has a shape. A receptor has a pocket. The shapes match, you smell. Keep that picture in mind. We are going to hand it a problem it was not built to hold. There has always been a second theory, quieter, older in its roots, dismissed for most of its life, and refusing decade after decade to die. It says the nose does not read shape at all, or not only shape. It says the nose reads vibration. To understand what that means, we have to go back before Buck and Axel, before Amour, to a chemist most people have never heard of. His name was George Malcolm Dyson. In 1938, in a paper in the Journal of the Society of Chemical Industry, Dyson proposed something his colleagues found close to absurd. He suggested that what makes a substance smell the way it does is not its shape, but its molecular vibration. Here is the idea, in plain terms first. A molecule is not a rigid little sculpture. It is a cluster of atoms joined by bonds, and those bonds behave like springs. The atoms are forever jittering, stretching, bending, rocking, twisting at specific characteristic frequencies. A carbon-hydrogen bond vibrates at one rate, a sulfur-hydrogen bond at another, a carbon-oxygen double bond at another still. Each kind of chemical bond has its own note, like a struck tuning fork. A whole molecule, with all its bonds, has a whole chord, a spectrum of frequencies as distinctive as a fingerprint. Chemists already knew this. They had been reading these vibrations for decades, using instruments that shine infrared light or laser light through a substance and measure which frequencies it absorbs or scatters. The pattern that comes back, the set of vibrational frequencies, identifies the molecule. It is called its spectrum. Dyson's radical leap was to suggest that the nose does the same thing. That somehow, biologically, the recipient is not feeling the molecule's shape, but sensing its vibrational spectrum. That smell, in other words, is a kind of spectroscopy. That your nose is, in some sense, a spectrometer made of flesh. Consider how strange a claim that is. A laboratory spectrometer is a precision instrument. It needs a light source, a detector, careful calibration. Dyson was proposing that a warm smear of nerve tissue does something equivalent in the time it takes to inhale. His contemporaries did not believe it. There was no known mechanism, no plausible way, a biological cell to perform a spectral analysis. The chemistry establishment set the idea aside, and for the better part of 2 decades it lay nearly forgotten. It did not stay entirely forgotten. In the 1950s, a researcher named R.H. Wright picked up the vibrational idea and tried to refine it. Wright argued that if the nose really did read vibration, the relevant frequencies could not be the high-frequency ones Dyson had emphasized. They would have to be low-frequency vibrations, far down in the infrared, because only those slow modes are strongly excited at the temperature of the body. It was a thoughtful adjustment, but Wright, like Dyson, had no mechanism. He could say which vibrations might matter. He could not say how a receptor would ever detect them. A theory of smell with no detector is like a theory of vision with no eye. It describes what should be seen, without explaining how anything sees it. Hold on to that gap, the missing detector. It is the hinge on which this entire story turns. For a while, the shape theory simply won. It had receptors, it had structure. After 1991, it had the full weight of molecular biology behind it. The vibrational idea became a historical footnote, the kind of thing mentioned in a lecture as an example of a clever guess that went nowhere. Then, in 1996, a biophysicist named Luca Turin walked back into the footnote and rebuilt it into something far harder to dismiss. Turin published a paper in the journal Chemical Senses with a title that stated his intent plainly: a spectroscopic mechanism for primary olfactory reception. In his own words, the theory proposes that olfactory receptors respond not to the shape of molecules, but to their vibrations. That much was Dyson and right again. But Turin added the one thing his predecessors had never had: a mechanism. A concrete, physical proposal for how a receptor could actually read a molecule's vibration. And it came straight out of quantum physics. The mechanism is called inelastic electron tunneling. We will build it carefully because it is the strange heart of this whole story, and because everything that follows, every experiment, every objection, every unresolved argument, turns on whether this mechanism can be real inside a living nose. Start with tunneling itself. In the ordinary world, if you roll a ball at a hill and it does not have enough energy to reach the top, it rolls back. It cannot pass. An electron is not a ball. In quantum mechanics, a particle is also a wave, a spread-out cloud of possibility. And that wave does not stop dead at a barrier. It leaks through. It thins as it crosses, but it does not vanish. And on the far side, there remains a small but real chance of finding the particle, as if the ball, now and then, simply appeared on the other side of a hill it never had the energy to climb. This is quantum tunneling. It is not a metaphor, and it is not speculation. It is measured every day. It runs the radioactive decay of atoms. It runs the microscopes that let us photograph single atoms. It is as established as anything in physics. We have looked at tunneling on this channel before, at how a particle crosses a barrier it should not be able to cross. And we will return to it here in a place no one expected to find it: the inside of your nose. Now make the tunneling inelastic. Imagine an electron tunneling across a tiny gap inside the receptor, from one site, a donor, to another, an acceptor. Ordinarily, the electron would cross only if the energy on both sides matched. But suppose the odorant molecule is sitting in that gap, and suppose the electron, as it tunnels across, can hand off a precise packet of its energy to the molecule, just enough to set one of the molecule's bonds vibrating. If the molecule has a vibration of exactly the right frequency to accept that energy, the electron completes its crossing. If it does not, the electron is stuck. The tunneling succeeds only when the molecule's vibration matches the electronic's needs to shed. The molecule's vibrational note becomes the key that lets the current flow. That is inelastic electron tunneling, and it is not exotic in the laboratory. Physicists have a tool built on exactly this principle. It is called inelastic electron tunneling spectroscopy, and it was first demonstrated in the 1960s. Send electrons tunneling across a junction with molecules inside it, and the current jumps at specific voltages, precisely voltages that match the molecule's vibrations. The device reads a molecule's vibrational spectrum by watching when electrons can and cannot tunnel. It is, in effect, a spectrometer that uses tunneling electrons instead of light. Turin's proposal, stripped to its core, is this. The odorant receptor is a biological version of that instrument. The receptor is not merely a pocket that feels shape. It is a tunneling junction. When the right molecule sits in the gap and offers a vibration of the right frequency, an electron tunnels, the receptor activates, and you smell. When the molecule's vibrations do not match, the electron does not cross, and the receptor stays silent. Turin called it, memorably, a swipe card model. A lock and key asks only whether the shape fits the slot. A swipe card reads information encoded in the card as it passes. The molecule, on Turin's view, is swiped, and what the receptor reads of it is not shape but vibration. In 2007, a group of physicists took Turin's idea and did what Dyson, Wright, and even Turin had not fully done. They tested whether the physics could actually work. Jennifer Brooks, Filio Hartutsiou, Andrew Horsfield, and Marshall Stoneham, working at University College London, built a mathematical model of odorant-mediated inelastic tunneling using realistic biological numbers and published it in Physical Review Letters, one of the most demanding journals in physics. Their conclusion was carefully worded and worth quoting in spirit. The mechanism was consistent both with the underlying physics and with observed features of smell, provided the receptor had certain specific properties. It was not proof. It was something subtler and, for the vibrational theory, more important. It was a statement from hard-nosed physicists that the idea was not obviously impossible, that the numbers, under the right assumptions, did not immediately fall apart. Notice the phrase, though, provided the receptor had certain properties. Underline it. We will return to those properties, and to whether a warm, wet, jostling biological cell can possibly have them. That single conditional clause is where the whole argument will eventually be won or lost. Let me pause here and place an equation into the record, because this audience appreciates seeing the machinery, and because one simple relation sits underneath everything we have said. It is the oldest equation in quantum theory, written by Max Planck at the turn of the 20th century. In words, energy equals Planck's constant times frequency. E equals h nu. Energy, E, Planck's constant, h, a fixed number of nature, and nu, the frequency of the vibration. What the equation says is that vibration and energy are the same currency. A molecular vibration of a given frequency corresponds to a packet of energy of a definite size. This is why a tunneling electron can, in principle, read a vibration at all. To excite a vibration of frequency nu, the electron must give up exactly the energy E that Planck's relation demands. The vibrational note and the energy step are locked together by a constant of nature. Keep that phrase, a constant of nature, somewhere in the back of your mind. We will need it much later when we ask why the constants are what they are. There is a second equation worth stating, because it is the reason this whole debate can be tested at all. A vibrating bond behaves like a mass on a spring, and the frequency of a mass on a spring is given by a relation from classical physics. The angular frequency equals the square root of the stiffness divided by the mass. Omega equals the square root of k over m. Omega, the frequency, k, the stiffness of the bond, m, the mass of the atoms doing the vibrating. Read that equation and something jumps out. Frequency depends on mass. Make the atoms heavier and the vibration slows. That single fact, that a heavier atom vibrates at a lower frequency, is about to become the sharpest knife in this entire fight. Because there is a way to make a molecule heavier without changing its shape at all. Remember that. We will come back for it. So here is where the neutral ground stands. Two theories, both serious, both defended by capable scientists. The shape theory says the nose feels the geometry of molecules, a lock and its keys, now crowned with a frozen photograph of a receptor cradling its target. The vibrational theory says the nose reads the trembling of molecules, a swipe card mechanism running on the quantum tunneling of electrons, defended by a biophysicist and given cautious physical cover by a team of physicists who found that under the right conditions it need not be impossible. What does it mean that the most intimate of the senses, the one that reaches us before language, the one wired most directly into memory and emotion, is also the one science cannot yet explain? We do not know how you smelled your morning. We have two stories, and they cannot both be the whole truth. For now, we hold both. We do not yet choose. We have laid out the hardware, the history, and the two rival readings of what recognition means. Now we go deeper, into the specific molecules that refuse to behave, the experiments that turn this from a quiet academic disagreement into one of the sharpest disputes in modern sensory science, and the exact point where a warm biological cell collides with the cold demands of quantum measurement. To decide between two theories, you look for a case where they predict different things. Smell offers two such cases, and they are the reason this argument has lasted 90 years instead of ending in an afternoon. The first is a molecule and its mirror image. The second is a molecule and its heavier twin. Hold each up to the light, and the two theories point in different directions. Begin with the mirror image. Take your two hands and press them together, palm to palm. They match. Now lay one flat on the other, both palms down. They do not. Your hands are mirror images, identical in every part, and yet not superimposable. Chemists call this property chirality, from the Greek word for hand. And molecules have it too. A great many molecules come in two versions, left-handed and right-handed, built from exactly the same atoms in exactly the same connections, differing only in that one is the mirror reflection of the other. Same formula, same bonds, same vibrational spectrum, because mirroring a molecule does not change how its bonds stretch and bend. The two hands play the same chord. Now the test. There is a molecule called carvone. Its right-handed form is the smell of spearmint. It makes up most of the oil in the spearmint leaf. Its left-handed form is the smell of caraway, the dark seed in rye bread. Spearmint and caraway. One molecule, two mirror images, two utterly different smells that no one would ever confuse. Sit with what that means for each theory. The shape theory has an easy answer and a hard answer folded together. Easy because two mirror image molecules have different shapes the way two hands have different shapes. A right hand will not fit a left glove, so a receptor pocket built with a handedness of its own could tell them apart. The proteins of your body are themselves chiral. A chiral pocket feeling a chiral key is exactly what shape theory expects. But the vibrational theory now has a genuine problem, and it is worth stating plainly rather than hiding, because we are still presenting, not prosecuting. If smell reads vibration, and the two carvones have the same vibrational spectrum, then the vibrational theory seems to predict that spearmint and caraway should smell the same. They do not. This is the single hardest fact the vibrational theory has to face, and its defenders know it. They answer that the receptor mechanism can still be sensitive to handedness, because the pocket that holds the molecule is itself handed. Shape and vibration, on that reading, are not rivals, but partners. The shape getting the molecule into the site, and the vibration being read once it is there. Whether that answer works is exactly the kind of question we are holding open. For now, log it as evidence. The mirror image molecules cut against the pure vibrational picture, and cut for shape. Then comes the second case, and here the knife turns the other way. Remember the equation from before. Frequency depends on mass. A heavier atom vibrates more slowly. There is a way to make an atom heavier without changing anything else about a molecule, without changing its shape, its bonds, its chemistry in any way a lock and key pocket could feel. You replace ordinary hydrogen with its heavier isotope, deuterium. Deuterium is hydrogen with a neutron added. Same single proton, same single electron, same chemical behavior, same size and shape to a very close approximation, but twice the mass. Swap every hydrogen in a molecule for deuterium, and you have built a near-perfect experiment. To the shape theory, molecule is essentially unchanged. The key still fits the lock, so it should smell the same. To the vibrational theory, the molecule has changed profoundly. Every carbon-hydrogen bond now vibrates at a markedly lower frequency, dropping by roughly 800 wave numbers when it becomes a carbon-deuterium bond. So, it should smell different. The two theories make opposite predictions about the same molecule. This is as clean as biology ever gets. So, what happens? The honest answer is that it depends on whom you ask, and on whether you ask a fly or a person. And this is where the field split into open warfare. In 2011, a team including Maria Isabel Franco, Luca Turin, Andreas Merschin, and the neurogeneticist Efthymios Skoulakis published a study in the Proceedings of the National Academy of Sciences. They worked with fruit flies, trained in a maze to approach or avoid particular odors. They reported that the flies could tell an ordinary molecule from its deuterated twin. More than that, flies trained to avoid the deuterated version generalized their avoidance to a completely different molecule that happened to share a similar vibration, as if the flies were responding to the vibration itself, not the chemistry. To the theory's supporters, this was close to a smoking gun. The shape of the molecule said nothing had changed. The flies behaved as though a great deal had changed. What could they be reading, if not vibration? 2 years later, in 2013, a group reported that the effect reached to humans. In a study in the journal PLOS One, researchers tested whether people could distinguish ordinary from deuterated musk molecules, large, heavy molecules used in perfume. They reported that trained subjects could. The statistics, aggregated across subjects, were striking. Here, it seemed, was the vibrational theory's prediction coming true in the one animal whose smells we care most about, ourselves. If the story stopped there, the vibrational theory would be ascendant. It does not stop there. 2 other lines of evidence point hard the other way, and they are just as carefully done. The first is older than the fly study. In 2004, the same year Buck and Axel received their Nobel, Andreas Keller and Leslie Vosshall at Rockefeller University ran a rigorous test of one of Turin's own striking claims. Turin had asserted that acetophenone and its fully deuterated version smell different despite being identical in structure. Keller and Vosshall took carefully purified samples and asked both untrained and trained people to tell them apart. The people could not do it reliably. On the molecule Turin himself had singled out, the prediction failed. Their paper was, in effect, a direct challenge. The vibrational theory makes a claim about human perception, and human perception does not cooperate. The second line is the most serious of all, and it did not come from psychology. It came from inside the receptor. In 2015, a large team led by the chemist Eric Bloch, with the computational chemist Victor Batista at Yale, the olfactory biologist Hiroaki Matsunami at Duke, and others, published a paper in the Proceedings of the National Academy of Sciences with a title that did not hide its verdict: The Implausibility of the Vibrational Theory of Olfaction. Their approach was decisive in method. Rather than argue about whether people or flies could smell a difference, they went to the receptors themselves. They took human and mouse odorant receptors, expressed them in the laboratory, and exposed them directly to ordinary and deuterated molecules. That included the very musk receptor, called OR5AN1, that should have been most sensitive to the effect, and a mouse receptor for sulfur-smelling thiols, called MOR244-3. If the vibrational theory were right, these receptors should have responded differently to the heavy and light versions. They did not. At the level of the isolated receptor, the deuterium made no difference. The molecule's vibration changed. The receptor did not notice. That is the shape of the evidence, and you can feel why the field never settled. Flies seem to smell the difference. Some human tests seem to find it. A careful one does not. And the receptors, tested in isolation, appear blind to it. Each side can point to real data. Each side has an answer for the other's data. The skeptics note that a deuterated molecule is not only heavier, but slightly different in how it dissolves and how enzymes in the nose might chew on it. So a perceived difference need not be vibrational at all. The defenders note that isolated receptors in a dish are not the same as a living nose. The argument does not resolve, because every experiment leaves a door open. What does it mean that the same clean test, heavy molecule against light, gives one answer in a fruit fly, another in a purified human test, and a third in an isolated receptor in a dish? Underneath the experimental war lies a deeper objection, and it is the one that matters most, because it is not about any single molecule. It is about whether the mechanism can exist at all inside a body. This is where we have to talk about temperature, and about a quantity most people have never heard of, that may quietly decide the whole question. Return to that laboratory instrument, the inelastic electron tunneling spectrometer, the real machine that reads vibrations by watching electrons tunnel. Ask a simple question about it. What conditions does it need to work? The answer is brutal for anyone hoping to find the same thing in a nose. These instruments operate near absolute zero. The classic measurements are made at the temperature of liquid helium, around 4 Kelvin, which is about minus 269 degrees Celsius, minus 452 degrees Fahrenheit. Some are pushed colder still, to fractions of a degree above absolute zero. They run in a hard vacuum, isolated from every stray vibration. Why so cold? Because heat is motion, and motion is noise. At room temperature, everything is already jiggling. The delicate signal of an electron shedding one precise packet of energy into one specific bond is drowned in the thermal roar of everything shaking at once. To read the vibration, you must first freeze the noise. Cool the world until it is nearly still, and only then can the tunneling electron's whisper be heard. Now, set that beside the nose. Your olfactory epithelium is at body temperature, 310 Kelvin, 37 degrees Celsius, 98.6 degrees Fahrenheit. It is not a vacuum. It is a warm bath of salt water and mucus and thrashing molecules. From the point of view of a spectroscopist, it is the worst possible place to try to read a vibration. Hot, wet, and loud. The vibrational theory asks us to believe that a mechanism physicists can only coax into working near absolute zero runs effortlessly billions of times in the warm chaos of a living cell. This is not a rhetorical flourish. It can be made quantitative, and here is the number that haunts the whole debate. There is a quantity called the reorganization energy, written with the Greek letter lambda, which measures, roughly, how much the surroundings of the tunneling electron rearrange and absorb energy as it crosses. For the swipe card mechanism to work as a clean spectral reader, that reorganization energy has to be very small. The estimates that make the theory function put it around 30 milli-electron volts, and analyses suggest it must stay below about 100 milli-electron volts for the mechanism to remain feasible at all. Now, compare that to the thermal energy present at body temperature, the average jostling energy available to every particle, given by the temperature times a fundamental constant called Boltzmann's constant. At 310 Kelvin, that thermal energy is about 27 milli-electron volts. Look at those two numbers side by side. The signal the mechanism depends on, about 30 milli-electron volts, the thermal noise it must be heard over, about 27 milli-electron volts. They are nearly the same size. The whisper and the roar are at the same volume. And it gets worse for the theory, because typical electron transfer processes in biology do not have reorganization energies of 30 milli-electron volts. They have energies of several hundred, even 1,000. In the language of the 2015 critique, the assumption of such a small reorganization energy in the receptor is, in their word, unprecedented. Nothing else in the cell behaves that way. The vibrational theory does not just need an unusual mechanism. It needs a mechanism finely poised at the exact edge where the signal barely rises above the thermal sea, and only there. Let me put an equation to this, because it names the enemy precisely. The relevant electron transfer rate is described by a relation developed by the chemist Rudolf Marcus, work that earned a Nobel Prize. In its shape, the rate of transfer depends on three things: the strength of the coupling between the two sites, the driving force pushing the electron across, and, sitting inside an exponential, which is where its power lives, the reorganization energy lambda, weighed against the thermal energy. When lambda and the thermal energy are mismatched, the rate collapses. When they are poised just so, transfer flows. The equation does not care about anyone's hopes for the theory. It says the mechanism lives or dies on a number, and that number, in a warm cell, sits at the razor's edge of the noise. Keep that razor's edge in mind. Later, we will ask what it means that a proposed sense should require conditions balanced so finely, and whether balance that fine happens by accident. Here, I want to widen the frame, because the vibrational theory does not stand alone. It belongs to a young and contested field with a provocative name: quantum biology. The claim of quantum biology is that certain living systems do not merely obey quantum mechanics in the trivial sense that all matter does, but actually exploit its stranger features, superposition, tunneling, coherence, to do their jobs. Two other cases are cited most often. In photosynthesis, there is evidence that the energy captured from sunlight may travel through the light-harvesting apparatus of certain bacteria with a quantum efficiency that has invited the language of coherence. In bird navigation, there is a leading hypothesis that some migratory birds sense the Earth's magnetic field through a quantum effect involving pairs of electrons with correlated spins, housed in a protein in the eye. Neither is fully settled. Both are serious. Both share the vibrational theory's central tension. They propose delicate quantum effects surviving in warm, wet, noisy biological matter, where the textbook expectation is that such effects should be destroyed almost instantly by the surrounding jostle, a process physicists call decoherence. Quantum smell is one member of a family of claims, all of which ask the same audacious question. Can life hold on to quantum coherence in a place far too warm to keep it? We have explored on this channel before the idea that the mind itself might reach into quantum processes, that consciousness could be more than the firing of ordinary matter. This is the same frontier, approached through the nose instead of the brain. Keep that resonance in mind. It will matter when we ask, near the end, what any of this implies about what we are. Now let me show you why the vibrational idea, for all its troubles, refuses to die. Because there is something almost eerie about where it points. Turn the theory around and look at what it claims your nose is doing. It claims your nose is reading the vibrational fingerprint of a molecule. That is spectroscopy. And spectroscopy is how we read the universe. Consider what an astronomer does. Point a radio telescope at a cold cloud of gas between the stars, thousands of light years away, and you cannot touch it, cannot sample it, cannot bring it to a laboratory. And yet we know what those clouds are made of in astonishing detail. We know because every molecule there broadcasts its identity in the frequencies of light it emits and absorbs, the fingerprint of its own vibrations and rotations. More than 9 in 10 of the molecules ever identified in interstellar space were identified this way, by their spectral signatures. In 2024, using the Great ALMA array in the Chilean desert, astronomers identified a complex organic molecule, a relative of alcohol, in a star-forming cloud called NGC 6334I, more than 1,000 light-years away, by reading 25 distinct rotational lines in its spectrum. No one visited, no one sampled. The molecule announced itself across 1,000 light-years in the language of its own vibration. That is precisely the language the vibrational theory says your nose speaks. The same physics we use to read the chemistry of a dying star at the far edge of the galaxy, the vibrational theory places inside your head, reading the chemistry of a cup of coffee. What does it mean that the deepest tool of astronomy, the reading of matter by its vibration, might be running, unnoticed, behind your face? Whether or not the theory is finally true, the parallel is the reason serious people cannot let it go. It is too beautiful and too strange to dismiss without proof. The strangeness is not only poetic, it has already been engineered. Researchers have begun building artificial noses that borrow the receptor's trick directly. At the University of Pennsylvania, a group led by A.T. Charlie Johnson grafted olfactory receptor proteins onto carbon nanotubes, cylinders of carbon a single atom thick, to make transistors that fire when an odorant binds. Devices of this kind have detected specific molecules at concentrations of a few parts per billion. One such sensor picking up a marker of skin cancer at around 25 parts per billion. Whatever the receptor is truly doing, it is sensitive enough that copying even part of it yields an instrument of remarkable power. I want to be careful here not to overstate how much we know, because uncertainty runs all the way down, even to how many things we can smell at all. In 2014, a widely reported study claimed humans can distinguish more than 1 trillion different odors. It was a striking number, and it spread everywhere. But it rested on a mathematical extrapolation from a modest experiment, subjects actually discriminating on the order of 150 odor pairs, stretched by a formula to 1 trillion. The physicist Marcus Meister and others showed that the method was unsound, that the same formula could be made to yield almost any answer at all. The trillion odor figure, repeated as fact, turned out to be a number resting on very little. I raise it because it is a warning that runs through this entire subject. In the science of smell, confident numbers often stand on soft ground. Keep that lesson close. We are going to need it when we reach the claims that reach furthest. Notice what has quietly happened as we have gone deeper. We began with a clean question, shape or vibration, and every layer we have peeled back has revealed not an answer, but a deeper uncertainty. The mirror molecules cut one way, the heavy molecules cut the other. The flies say yes, the careful human test says no. The isolated receptors say no. The living nose remains unread. The mechanism is possible on paper and nearly impossible in the warmth of the body. And the men and women who have spent their careers on this, Turin, Bloch, Vossel, Brooks, Matsunami, agree on almost nothing except one thing, which we will now bring into the light. They agree that they do not actually know. What does it mean that after 90 years, the experts' one point of consensus is the depth of their own ignorance? That admission is not the end of the science. For us, it is the doorway to the harder question underneath it all. Before we cross into that harder question, we have to go one layer deeper into the machinery, because the argument that follows will lean on exactly how the proposed mechanism is supposed to work, and on exactly why it is so hard to catch in the act. First, the scale of the thing. Because it is easy to picture a single receptor meeting a single molecule and miss how vast the system actually is. You do not have one kind of smell detector. You have on the order of 400 distinct working receptor types, and no single one of them is a labelled slot for a single odour. The insight that earned Buck and Axel their prize was that smell runs on a combinatorial code. A given odorant switches on not one receptor, but a particular subset of them, and a different odorant switches on a different overlapping subset. The brain reads the pattern. This receptor yes, that one no, this one weakly. The way a word is read from a pattern of letters rather than a single symbol. With 400 receptors switching on and off in combination, the number of distinguishable patterns is astronomical, which is how a few hundred detectors can, in principle, register an enormous range of scents. And the number of detectors is itself a matter of biological investment. Humans carry roughly 400 functional odorant receptor genes. A mouse carries around 1,000. A dog, bred and evolved for the nose, carries more than 1,000, on the order of 1,100 working genes, which is part of why a dog reads a lamppost the way you read a page. The receptor family is one of the largest in the entire genome. Whatever smell is, the body spends lavishly on it. That vast apparatus is what the two theories are really fighting over. John Amour, building the shape theory in the early 1960s, tried to organize the whole of scent into a small set of primary odors, each tied to a molecular shape. An elegant idea, combinatorial code later complicated but never erased. R.H. Wright, defending vibration in the same era, argued that the relevant molecular notes had to be the slow, low-frequency ones, down in the far infrared, because only those are strongly stirred at the warmth of the body. Two traditions, shape and vibration, each trying to explain the same 400 detectors, and each, remember, still lacking the one thing that would settle it. A direct look at what a single receptor does at the instant it recognizes its molecule. Hold that scale in mind as we go deeper. The mechanism we are about to examine has to run correctly across hundreds of receptor types at once, billions of times a day. Return to the tunneling electron and ask a sharper question. What decides whether it crosses? In quantum mechanics, the rate at which a particle makes such a transition is governed by a relation known as Fermi's golden rule. In words, the transition rate is proportional to the strength of the coupling between the two states squared, multiplied by the number of available final states at the right energy. The rate is a product of two things: how strongly the starting point and the destination are linked, and whether there is a landing site waiting at precisely the energy the electron will have after it sheds its packet. For the swipe card mechanism, that landing site is the odorant's vibration. If a vibration of the right energy is there to receive the electron, the crossing lights up. If not, the rate falls toward nothing. Fermi's golden rule is the reason the mechanism can be selective at all. It is a rule about matching, and matching is the whole idea. Then there is the crossing itself, the tunneling, and it obeys a relation from the early days of quantum theory called the WKB approximation. Its content can be said simply, even if its mathematics is heavy. The probability that a particle tunnels through a barrier falls off exponentially with the width of the barrier and with the square root of its height. Double the gap, and the chance of crossing does not halve, it plummets. This is why tunneling is so exquisitely sensitive to distance, and why the geometry of the receptor matters so much to the vibrational theory. The donor and acceptor sites, the launch point and the landing point for the electron, must sit at just the right separation. Too far, and no electron ever crosses, the current dies. Too close, and the molecule's vibration becomes irrelevant, because the electron sails over regardless. The mechanism requires a gap tuned to a fraction of a nanometer. Another precise condition, stacked on the ones we already have. Keep the tower of conditions in view. It is growing. Underneath all of it sits the reason any of this talk of an electron being a wave is legitimate in the first place. It is the relation Louis de Broglie wrote in the 1920s, that a particle has a wavelength equal to Planck's constant divided by its momentum. Lambda equals h/p. It is the sentence that made tunneling thinkable, that told us an electron is not only a tiny ball, but a spread-out wave. And a wave can do what a ball cannot: leak through a wall. Without de Broglie's insight, there is no tunneling. And without tunneling, there is no vibrational theory of smell. The whole audacious idea rests on the wave nature of matter, one of the most thoroughly confirmed facts in all of physics. That is what makes the theory so hard to dismiss out of hand. Its foundation is not fringe. Its foundation is bedrock. It is the application that is daring, placing bedrock quantum mechanics inside the warm machinery of a cell. Now watch what happened when the two camps met head-on, because the exchange tells you everything about why this cannot be settled by shouting. When Eric Bloch and his colleagues published their case for the implausibility of the vibrational theory in 2015, Luca Turin and his allies did not concede. They replied in the same journal that Bloch's conclusion was premature, that testing receptors in a dish, stripped out of the living tissue and its supporting cast of molecules, was not the same as testing smell as it actually happens. Bloch answered in turn, and his answer is worth hearing in full spirit, because it names the real void at the center of the field. There is, he wrote, no experimental data at the molecular level showing direct evidence of electron transfer, or of the effect of odorant vibrations being responsible for triggering the receptor's response. Read that slowly. Not that the evidence is against it, rather that at the molecular level, the direct evidence for the mechanism does not exist. The mechanism has never been caught in the act inside a real receptor. It has been modeled, argued, inferred, made plausible, made implausible, but never directly observed. Leslie Vosshall, surveying the exchange, titled her commentary with a verdict: laying a controversial smell theory to rest. And yet it did not rest. Papers kept coming. The corpse kept sitting up. Why can it not be settled? Because of a wall of measurement that may be, for now, simply impassable. To catch the mechanism directly, you would want to do to a living receptor what the laboratory does to molecules on a cold junction. Watch the electrons tunnel. Read the vibrational steps in the current. But you cannot get an instrument in there. You cannot place the tip of a tunneling microscope inside a functioning receptor buried in the membrane of a living cell in a living nose. The scales are wrong. The environment is wrong. The act of measuring would destroy the thing measured. A funded effort led by Andreas Merschin and collaborators tried to push scanning tunneling spectroscopy toward exactly this question, and reported, honestly, that at the resolution and noise levels available, no significant variation could be found that could be tied to the presence of the odorant. That is not a refutation. It is something more sobering. an admission that our finest tools cannot yet reach the place where the answer lives. The direct experiment, the one that would end the argument, has never been done, because no one yet knows how to do it. There are further wrinkles, and each one deepens the fog rather than lifting it. The skeptics point out that a deuterated molecule differs from its ordinary twin in more ways than vibration alone. The enzymes that live in the nasal mucus, the perireceptor machinery that chews up odorants after they arrive, may act on the heavy molecule slightly differently than on the light one. That means a perceived difference in smell could be a difference in chemistry, in how fast the molecule is broken down, rather than a difference read directly off its vibration. So even the fly and human results that seem to favor vibration have an escape hatch the shape theory can crawl through. And the defenders have their own counters. For the mirror image problem, some have built more elaborate models. A dissipative quantum treatment proposed in 2015 by Tirandaz, Garamani and Shafi'i, that tries to show how a tunneling mechanism could, after all, distinguish left-handed from right-handed molecules if the receptor site itself is handed. For the musk experiments, the argument runs down into the specific vibrational bands. One heavy musk was said to lack precisely the frequency range, around 1,400 to 1,550 wave numbers, claimed to be essential for the musk smell. Every claim spawns a counterclaim, and every counterclaim a counter-counter, and the tower grows in both directions at once. Step back from the detail and feel the shape of the thing. This is what a genuinely unsolved problem looks like from the inside. Not a clean gap in a nearly finished picture, but a live, churning dispute in which capable people, using the best tools available, cannot force nature to give a straight answer, because the answer lives in a place the tools cannot reach. And the frontier keeps moving. As recently as 2025, physicists were still publishing on what they called quantum smell, modeling odorants as weak tunneling conductors operating in what they termed a deep, off-resonant regime. New mathematics, new framing, the question still open, nearly 90 years after Dyson first suggested a nose might read a spectrum. The idea has outlived its author, outlived its first champions, survived a formal declaration of its own death, and walked into a new century still refusing to resolve. I find I return to one image more than any other. We take on the order of 20,000 breaths a day. Each one is a measurement. Each one sorts a drifting chemistry of the world and hands us a result. Safe, spoiled, sweet, burning, familiar, gone. Faster than thought, beneath the reach of will, by a mechanism that the sharpest instruments and the sharpest minds cannot yet write down. This is the part that stays with me, not the exotic physics, ordinariness of it. That the most unsolved problem in this whole story is not out at the edge of the galaxy, but at the center of your own face, running quietly, all day, every day, unexamined. What does it mean that the deepest mystery you will meet today is the smell of your own coffee? There is a limit here that no instrument will ever cross, no matter how the mechanism debate resolves. Suppose someday we do get the tip into the receptor. Suppose we read the tunneling steps and settle shape versus vibration once and for all. We will have solved the detection. We will not have touched the sensation, the actual, private, unrepeatable experience of the scent as it blooms in your awareness. That is a different kind of unknown, not a gap in our instruments, but a gap in the whole materialist account, and it is the one we turn to now. Because it is here, at the boundary between the mechanism and the experience, that the science hands off to the deeper question, the one about what we are, and what could possibly have made a thing that not only detects the world, but feels it. For a long while now, I have laid out what scientists claim, and I have laid it out fairly, without pushing back. That was deliberate. You have seen the shape theory and the vibrational theory, the flies and the receptors, the razor's edge of thermal noise, and the parallel to the reading of distant stars. Now the work changes. Now we examine. Not the science itself. The science is honest, and the uncertainty is real. What we examine are the larger claims that get draped over the science, the philosophical conclusions that certain voices insist the facts require. Those claims deserve the harder look, because they are where the reasoning quietly fails. We will take them one at a time, give each its strongest form, and follow it until it breaks. Start with the claim you hear most, stated with the most confidence. It goes like this: smell is just chemistry, just physics. A molecule, a receptor, a cascade, a spark. Mechanism all the way down. And once we finish the mechanism, there will be nothing left to explain, and certainly no need to invoke anything beyond matter. The whole of your inner life, this view holds, is chemistry that has not yet been fully diagrammed. No design, no purpose, no maker. Only molecules doing what molecules do. Give that claim its due. It is not stupid, and many thoughtful people hold it. It has the momentum of 3 centuries of success behind it. Every time science has chased a mystery, it has found mechanism. And the mechanism has never once turned out to be a spirit hiding in the gears. So the expectation that smell, too, will reduce to pure mechanism is not a prejudice. It is an extrapolation from a long winning streak. Now examine it, and examine it on its own terms. The claim is that smell is just chemistry we have essentially figured out. Is it? Return to the people who have actually done the work, not the popularizers, the practitioners. In 2015, the very paper that argued most forcefully against the vibrational theory, the Bloch critique, stated in plain print that neither the structures of the odorant receptors, nor the binding sites, nor the activation mechanisms triggered when an odorant binds have been established. That is the skeptic speaking, the defender of the mainstream shape theory, admitting the mechanism is not established. In 2023, the very team that produced the triumphant frozen photograph of a receptor holding its target wrote, in the same paper, that how odorants are recognized by odorant receptors remains unclear. The people holding the clearest picture ever taken said, in the caption, that they still do not fully understand what they are looking at. And back in 2007, one of the physicists who modeled the tunneling mechanism conceded that the full significance of the idea could only be judged after much more experimental work. Here is the first fracture, and it is not subtle. The claim is that smell is just chemistry, already essentially solved, no mystery requiring anything further. The scientists who know the most say the mechanism of recognition is unestablished, unclear, unresolved. The confidence lives entirely in the popular telling. It evaporates the moment you reach the laboratory. This is the rhetorical move the philosopher would call the promissory note, the assurance that science has explained, or will surely soon explain, a thing it has openly not explained. A promissory note is not payment. Watch how the claim actually works. It does not point to a completed explanation. It points to the confidence that one is coming. That is not a conclusion drawn from evidence. It is faith. Faith in a future discovery, wearing the costume of established fact. Notice this. It is the same structure atheists rightly criticize when they accuse the believer of a god of the gaps, of stuffing a deity into whatever science has not yet explained. Turn the accusation around because it cuts both ways. When someone says the origin of smell, or of life, or of consciousness is unexplained now, but will surely yield to matter alone later, they are performing a naturalism of the gaps, stuffing an unproven materialist explanation into exactly the space where no explanation yet exists. The gap is the same gap. The faith is the same faith. The only difference is the name written over the empty space. Intellectual honesty demands we notice that the person most certain smell is just chemistry is standing in front of a mechanism that, by the expert's own testimony, no one has established. That clears away the false confidence. But it does not yet reach the deeper claim. So let us go there, to the place the whole materialist story runs out of road. Grant, for the sake of argument, everything the mechanists want. Grant that one day we will have the complete diagram. This molecule, this pocket, this electron crossing this gap, this vibration accepted, this channel opening, this neuron firing, this signal arriving in the brain. Grant the entire chain, every link forged and photographed. Now answer one question. Where in that diagram is the smell? I mean the smell itself, the warm, unmistakable, wordless presence of coffee. Not the wavelength of a vibration, not the voltage of a spike, the experience. What it is like from the inside to smell. You can trace the molecule to the receptor to the current to the cortex, and at the end of that entire physical account, you will have described everything except the one thing that actually happened to you. That you smelled coffee and knew it, and were somewhere for a moment because of it. Philosophers call this the hard problem of consciousness, and it is at its very hardest in smell, the most feeling-drenched, memory-soaked, least verbal of the senses. No arrangement of unconscious particles has ever been shown to produce, or even to imply, the felt quality of an experience. You can build the most complete mechanical story imaginable, and the smell will not be in it, any more than a wiring diagram contains music. This is the claim that quantum biology is sometimes recruited to defeat. The claim that if we can just push the mechanism deep enough, down into the quantum level, we will finally show that mind is nothing but matter after all. Look what that hope actually does. It does not close the gap, it relocates it. Suppose the vibrational theory is completely vindicated tomorrow. Suppose your nose really is a tunneling spectrometer. You have then explained the detection more deeply. And you have explained the experience not one particle further. A tunneling electron is exactly as unconscious as a docking molecule. Pushing the mechanism from chemistry down to quantum physics changes how the signal is read. It does nothing whatever to explain how the reading becomes a feeling. The materialist has moved the mystery to a smaller room and locked the door, and called that a solution. Follow the materialist claim to its end, and it consumes itself. If your experience of smelling coffee is nothing but molecules in motion, with no reality of its own, then so is your thought that it is nothing but molecules. The argument, if true, dissolves the very reasoning that produced it. A chain of mere chemistry has no claim on truth, only on having happened. A conclusion that undercuts the possibility of reaching conclusions is not a conclusion. It is a self-inflicted wound. The one fact you are surest of in all the world, that right now something is happening to you, that there is an experience of reading these words, is exactly the fact that a universe of only unconscious matter cannot account for. The smell you cannot doubt is the thing the mechanism cannot explain. Now to the deepest claim of all, and the one that reaches at last out past the nose and into the structure of the cosmos. It is the claim that all of this, the receptor, the mechanism, the sense, animal that carries it, is the product of blind processes needing no designer. Chance and time and selection and nothing else, and certainly nothing intended. Let us give that claim its strongest footing, and then test it where it is weakest. Return to the razor's edge, the number I asked you to keep. For the vibrational mechanism, even to be possible, a certain quantity had to sit in an exquisitely narrow band, the reorganization energy poised near the thermal noise, the signal balanced against the roar within a hair. Set that aside as merely suggestive, if you like. Go instead to something far more fundamental, something that holds whether smell reads shape or vibration or both. Go to the vibrations themselves. Every molecular vibration we have discussed, every note in every chemical chord, the carbon-hydrogen stretch, the spearmint chord, the whole spectrum your nose or a telescope might read, has the frequency it has because of the fundamental constants of physics. The stiffness of a chemical bond is set by the strength of electromagnetism, which is fixed by a pure number called the fine structure constant. The frequency of a vibration depends on the masses of the atoms and ultimately on the ratio between the mass of the electron and the mass of the proton. Write the relationship and it is stark. The electronic energies scale with the square of the fine structure constant. The vibrational frequencies scale with the square root of the mass ratio. Change those constants, and every vibration in chemistry shifts. Change them enough, and the delicate architecture of stable molecules, the bonds that hold a receptor together, the bonds that make an odorant, the bonds that make you, does not merely sound different. It ceases to be possible at all. Physicists who have mapped this out describe a narrow habitable zone in the space of these constants, a small region where matter can form the stable, complex, information-bearing molecules that life requires. Step outside it, and there is no chemistry to smell, and no one to smell it. Here is the anti-theistic reading of that fact, stated at full strength. The constants simply are what they are. We happen to exist in the one arrangement that permits us. And to be impressed by this is like a puddle, marveling that its hole fits it so perfectly. And if one asks why the constants are so finely poised, the deepest naturalist answer is the multiverse. Perhaps there are countless universes with every possible setting of the constants, and we unavoidably find ourselves in one of the rare few where observers can exist. No design, just an infinity of tries and a survivor's eye view. Examine it. Take the multiverse first, because it is offered as the trump card. What is the evidence for these other universes? There is none. Not one has been observed, measured, or detected, and by the nature of the proposal, none can be. It is invoked precisely and only to absorb the appearance of fine-tuning, an unlimited supply of unseen worlds conjured to explain away the calibration of this one. Weigh that honestly. When a theist proposes an unseen cause to explain the order of the universe, the materialist objects that the cause is unobservable and therefore not science. But the multiverse is unobservable in the very same way, an unfalsifiable posit adopted for the express purpose of avoiding a conclusion. That is not science defeating faith. That is one act of faith substituted for another, with the added cost that it explains nothing else and predicts nothing at all. And even granting it, the problem only moves. Whatever machinery generates the endless universes, with whatever laws let it do so, would itself require explanation. You have not escaped the need for a cause. You have multiplied it without limit. And the puddle? The puddle analogy is clever, and it fails for a precise reason. A puddle fits its hole because water is a passive liquid that flows to fit whatever container it lands in. The fit is imposed by the hole onto something infinitely adjustable. But the constants of physics are not water poured into life. They are fixed at the foundation of everything, before there is any chemistry at all. And life is the fragile, exacting thing that can exist only if those fixed numbers already fall within the narrowest of ranges. The order of dependence is reversed. The puddle adapts to the hole. Here, the hole had to be cut to fantastic precision before the water could exist to fill it. What the analogy hides is exactly the thing that needs explaining. Not that we fit the universe, but that the universe was fit to be fitted. So follow the evidence where it actually leads, without flinching in either direction. We are asked to believe that the constants which permit stable molecules fell by accident into the one narrow band that allows them. That from those molecules, by chance alone, assembled the most sophisticated chemical detector known, a receptor so refined that copying a fragment of it yields an instrument sensing single molecules, and that this detector then produced, by unguided steps, the inward experience of smelling, a felt awareness that the most complete physics cannot locate in its own equations. Chance for the constants, chance for the machinery, and for the awareness, a promissory note. That is 3 miracles in a trench coat, asking to be called the sober scientific view. What does it mean that the view claiming to have banished the miraculous requires 3 unexplained leaps to hold itself together? Let me ground this where you live, because it is easy to lose the thread in constants and receptors. Think of a master craftsman's workshop, a watchmaker, say, building an instrument of impossible fineness. When you find such an instrument, gears meshed to a tolerance you can barely measure, every part shaped for a function, the whole thing keeping time, you do not conclude that the metal fell into that arrangement because, given enough valleys and enough centuries, some heap of ore somewhere had to. You infer a maker, and you infer the maker's attributes from the work: skill, knowledge, intent. This is the plainest inference human beings make, and we make it 100 times a day without a second thought. Now the analogy and the honest place where it strains. Someone will say the watch is a poor comparison because we have seen watchmakers and we have never seen the maker of a receptor. That is true, and it is exactly where the everyday picture must be pushed harder, not dropped. We infer the watchmaker not because we watched him, but because the watch carries the unmistakable marks of intention, parts arranged for an end, information expressed in matter. The odorant receptor carries those same marks, and more of them, at a level of miniaturization no watchmaker ever approached, storing and reading molecular information by a mechanism we cannot yet fully write down. The point where the analogy seems to break, that we never saw the maker, is the very point the design inference was built to cross. We have never seen the maker of anything at the foundations. We read the maker, as we always have, off the made thing. And the made thing here is a spectrometer of flesh. What does it mean that the instrument inside your nose outperforms the instruments in our finest laboratories, running warm and wet and silent, where ours need vacuum and a temperature near the end of all motion? What does it mean that the reading of matter by its vibration, the very tool by which we decode the chemistry of galaxies, appears to have been placed, working, inside a living skull, long before any human built the cold machine that struggles to imitate it? The materialist says coincidence, accident, the puddle admiring its hole. But we have now watched that answer fail 3 times over. Fail to explain the calibration, fail to explain the mechanism, fail utterly to explain the experience. And when the answer that claims the authority of science cannot survive its own cross-examination, honesty requires us to say so, and to name the alternative it was invented to avoid. The alternative is not complicated, and it is not a retreat into ignorance. It is the reading of a made thing back to its maker. A precision this deep did not set itself. A mechanism this refined did not assemble itself from nothing with nothing intending it. And an inner experience, the felt reality of a scent, cannot arise from what has no inwardness at all, unless inwardness was there in the source to begin with. Power to fix the constants at the foundation of the world. Knowledge to specify a chemistry that could build a reader of chemistry. And will, because a configuration was chosen out of the boundless configurations that were not. Those are not the properties of unconscious matter. They are the properties of a mind. The evidence, examined honestly and followed without fear, points in one direction, not to a gap where God is hiding, to a design whose author signed his work in the very thing we least understand and carry with us into every room and use without thinking each time we breathe. Let me bring this exploration to a close. We began with a breath and a measurement you never noticed, a drifting molecule caught in the warm dark behind your face, sorted and named before you could speak. We laid out two rival stories of how that naming happens. The shape theory, where the nose feels the geometry of a molecule, a lock and its key, crowned now by the frozen photograph of a receptor cradling its target. The vibrational theory, where the nose reads the trembling of molecules, George Dyson's old Spectrometer of flesh, rebuilt by Luca Turin on the quantum tunneling of a single electron, given cautious cover by the physicists who found the mechanism was not, on paper, impossible. We followed the mirror molecules and the heavy molecules, the flies that seemed to smell the difference and the receptors that seemed blind to it. We stood the whole idea against the razor's edge, where the signal barely rises above the thermal roar of a warm cell. And we heard the practitioners, Bloch, Billisböhle, Vosshall, Turin alike, agree on one thing only, that they do not yet know. Then we asked what the not knowing means, and we watched three confident answers fail. That smell is just chemistry, refuted by the chemist's own admission that the mechanism of recognition is unestablished. That mind is just matter, refuted by the plain fact that no diagram of molecules, however complete, contains the felt experience of a scent. That all of it arose by blind accident, refuted by the exquisite calibration that lets stable molecules exist at all, and by the multiverse's failure, an unseen infinity conjured for the sole purpose of explaining that calibration away. What remains when the failed answers are cleared is not ignorance, it is inference. A precision this deep did not set itself. A reader of chemistry this refined did not assemble itself from nothing with nothing intending it. And an inner experience, the wordless reality of coffee, of rain, of a face you love, cannot rise from what has no inwardness at all, unless inwardness stood at the source. Power to fix the constants, knowledge to specify a chemistry that could build a sense, will, because one configuration was chosen from the countless that were not. Those are the marks of a mind. The evidence, followed honestly, points there, not to a gap where a God hides, but to a design whose author signed his work in the very thing we understand least and carry into every room. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. And if one thread refuses to let you go, let it be this one. At the heart of the vibrational theory sat a single electron, crossing a barrier it had no business crossing, slipping through a wall instead of over it. I have followed that one impossibility much further on its own, the strange physics of how a particle passes through what should stop it cold. If that question stayed with you, you will find where it leads on the end screen now and in the description. Sleep well tonight, breathing a world you read more deeply than you know. Each quiet inhalation, a measurement our finest machines can barely imitate, running warm and silent behind your face. In a sense so old and so intimate that we have spent 90 years, and still counting, learning that we do not understand it at all. Good night.